Okay, continuing on another part of the final exam review. For number 20, you're going to refer to the chapter 12 notes and look up phase changes and, what is sublimation, what is condensation, all that kind of stuff. For number 21, our solid is our lowest kinetic energy, liquids are in between, below, medium, I guess you would say, and then gas has the greatest kinetic energy. 22, those are the answers to those questions. Let me know if you have questions. Number 23, you need to understand phase diagrams. So if you look at your phase diagram in your packet, it shows you the solid, liquid, gases, the triple point, the different state phase changes on that diagram. And for number 23, for number 23, we can talk more about that in class if you have questions. For 24, number 24 is the point at which the liquid and gas phase are indistinguishable. So that's the critical point on the phase diagram. That's that line at the end of the liquid and gas phase. 23, again, you'll need to review to the packet for that. Number 25, you're going to need to review for your review packet. I'm sorry. Number 26 is 1 ATM. 27 assumes that particles are in a constant random straight line motion. That's kind of the a summary of the kinetic molecular theory that you will need for your test. Number 28 is a Dalton's law problem. I'm sorry, not a Dalton's law problem. It is a mole fraction problem. So you add up the parts that they give you. So they give you the mole fractions of each part. You add them up, you get a total of 0.944. All of these together should add up to 1, but you're missing one. So the missing one, which is argon, can be found by taking the total, which is 1, minus all of the parts that were added together, and that gives you the part that was argon. So it's really just adding and then subtracting this total from 1. Number 29 is nonpolar covalent. So like dissolves like, so substances that are similar on a molecular level in terms of polarity will mix. So a nonpolar substance would combine easily with another nonpolar substance. Number 30 is a molarity problem. So they give you grams, which need to be converted to moles first, and then once you have moles, you divide it by the volume, which gives you molarity, because molarity is in moles per liter. Okay, for question 31, acids will produce hydrogen ions in solution and bases will produce hydroxide ions in solution. And for number 32, strong acids completely ionize in solution and transfer hydrogen ions to water to form H3O. So it's that hydrolysis where hydrogen is donated to the water. Remember, hydrogen ion donor for acids is a proton donor. Bases are proton acceptors, forming the H3O plus and the chloride ion for this particular reaction. Okay, just a rundown of the properties of acids and bases. Acids taste sour, they turn blue litmus paper red, they have a pH less than 7, and bases are bitter, turn red litmus blue, they feel slippery, they have a pH greater than 7. And number 34 is a measure of pH. Okay, measure pH is the best way to determine if it's an acid or a base. And 35, strong acids react with water to form H3O plus, which is the hydronium ion. That's that reaction that was just on the previous slide. And number 36 is called a neutralization reaction. 37, remember the endpoint should be at the equivalence point and the indicator changes color at this endpoint. Okay, for number 38, it's asking you if a pH changes from 4 to 2, how does that affect the hydronium ion concentration? Remember, pH is a measure of the H plus or the hydronium ion concentration. And so if we have a pH of, say, 1, our concentration be 1 times 10 to the negative 1. If we take the negative log of this, it gives us a pH of 1. If we take the negative log of this, we get a pH of 2. Negative log of this, we get a pH of 3, and so on. So every time we're moving over here on this pH scale, we're actually increasing or decreasing, depending on which way we're moving, the H plus concentration by a factor of 10. So this is 10 to the negative 1, move the decimal over one more place to the negative 2, negative 3, and so on. So these are all varying by a factor of 10. So if we go from a pH of 4 down to 2, 4 to 3 would be a 10 times difference, and then 3 to 2 would be another 10 times difference. So 10 times 10 is 100. It's 100 times difference if you move 2 spots over on the pH scale. Number 39, this is a time where you're going to have to use your pH equations, but you do need to be aware that this base, for every time it dissolves in water, it splits up into strontium and 2 hydroxides. So before we plug it into the pH equation, we need to double its concentration. All right, so it's equal to 2 times 0.25. So we're really going to be plugging in 0.5 molar for our hydroxide ion concentration instead of 0.25 because we have double the amount of hydroxides here. So when we do that, we get a pOH of 0.3. Number 40, this is Le Chatelier's principle, and I'm going to make a separate recording for Le Chatelier's principle and for oxidation reduction because we did not cover those topics yet. So I'll make a separate recording that goes through a tutorial of those topics. Number 41, and by the way, the answer to number 40 is shifts to the right to produce products, but you won't understand what that means. 41, same thing, it's an equilibrium problem. So the answer is it shifts to the side with the fewest number of moles. 42 is C, again, another equilibrium problem. And 43 is temperature, concentration, and pressure, another equilibrium concept that we will discuss in a separate recording. For 44, again, equilibrium, so it's a shift right. B is shift right, and C is also shift right. 45 is the second topic that I'm going to be making a second recording over, and that is oxidation reduction. Just a quick rundown. Oxidation is the losing of electrons, and reduction is the gaining of electrons. So if something loses electrons, it's considered to be oxidized. If something has gained an electron through a chemical reaction, it is said to be reduced. An easy way to remember this is oil rig. Oxidation is losing, reduction is gaining. And in 46, one element is oxidized while the other is reduced. Again, I will go through these problems in more detail in a separate recording. So again, 47, here's the answer to this problem. Again, I will do this in a separate recording so that I can describe this process that I used here. But that's the answer anyways, and you can refer back to that. You can skip question 48. 49 is a energy problem. So just all the specific heat stuff we've been doing. So you take the mass of oxygen and you convert it to moles. And then using your balanced chemical equation, for every 5 moles of oxygen that were reacted, this much energy was released. So you can say that the answer is negative 1.6 kilojoules, or that there were 1.6 kilojoules of energy released. So this is your gram to mole, mole to energy problem when they give you a balanced chemical equation with the delta H value. Okay, you can skip question 50. Question 51, how do catalysts speed up the rate of chemical reaction? Well, they speed it up by decreasing the activation energy required to get the reaction going. 52, they change spontaneously with lower energy and higher entropy. So just know this, entropy is a measure of disorder in a system. So if we want spontaneous changes, we want to move towards lower energy, which would be like a negative delta H value, and higher entropy. And entropy is a measure of disorder. So those are the two factors that determine whether or not a chemical reaction will be spontaneous. 53, we've been working with this recently. Q equals mass times specific heat times delta T. And you just plug the values in and you get negative 81,000 joules. For number 54, again, we use the Q equals mass times specific heat times delta T, and we get this value. The value for specific heat in question number 4 wasn't given to you. It was actually given to you in question number 53. So it's 0.45. That value will be given to you on the final exam. That's the specific heat of iron for both of these. Number 55, again, Q equals mass times specific heat times delta T, and that is our value when we solve for delta T.